So this is a tutorial on how to solve equilibrium problems while using ice tables. Equilibrium problems really aren't overly difficult to solve when the system's already at equilibrium, but oftentimes we don't know the equilibrium values until we do some math to figure those out. And the math that we do those with would be using an ice table. Now, ice doesn't actually mean ice, it means instead initial change in equilibrium values of that equilibrium system. Um, Equilibrium ice tables are going to be used with an equilibrium expression. It's just we need to get the equilibrium values. So we're still going to want to write an equilibrium expression, and we're going to use the ice table to then substitute values into the equilibrium expression, and then we'll solve for whatever the problem's asking for. So the easiest way to show this is just to use a example problem of how to use an ice table. And I'm going to start by going ahead and writing out my equilibrium expression for this system here. This is a gas. It says that in the problem. It should probably actually say that in the equation, but we can figure that out from the problem. So we know that both of these substances will be uh, in our equilibrium expression. Recall that the products go on top. So the concentration of my nitrogen dioxide, it's going to have a power of 2 from that coefficient, and then the concentration of my N2O4, which has a power of 1. What I'm looking for are the values that go in here. This system does not say it's currently at equilibrium. It says after reaching equilibrium, the concentration of NO2 is 0.0068, but we need to figure out the concentration for both of these substances. So we have to use an ice table. To do that, you're going to set up a grid that looks something like this. We're going to write down ICE along the left. There's the ice that makes up our ice table. And then we're going to put our two substances that we have. Now, we have a left side of an arrow and a right side of the arrow, and those are going to do some different things inside of our ice table. We're going to start by writing down the N2O4, and then the NO2 will be on the right side. This is a reactant, this is a product. So we need to think about what that means for the quantities of these chemicals. In a reactant, or for a reactant, the initial values will be given to you in the problem, or it's possible you might need to solve for them. The initial value of product is always going to be 0 because before reactions happen, there can't be any product. If we place the 0.0774 moles in a 1 liter flask, that's telling us that we have 0.0774 divided by 1, so that's going to be the molarity of our chemical. That's our initial value. Now, if we start out with this much, there's no way we can finish with this much when we've reached equilibrium. So the only thing that this 0.0774 can do is decrease. That means that the change of our reactants will always be negative. The change of our products then will be positive because 0 can only increase. And then finally, I want to check my mole ratios in front of my two substances. I have 1 mole in front of the N2O4, and I have 2 moles in front of the NO2. This mole ratio can come into play when we're looking at our change because these will change in a stoichiometric ratio. The problem goes on to say that after reaching equilibrium, the concentration of NO2 is 0.0068. So NO2 at equilibrium, 0.0068. I'm putting this down the bottom row because this is at equilibrium. E stands for my equilibrium values. To go from 0 to 0.0068, my change was 0.0068. Now we said that this change is going to be stoichiometric. So that means it's going to have to change in a 1 to 2 ratio. We can do the quick stoich to show how that works by setting up a factor-label problem. If I take my change, 0.0068, and that is big M of NO2, it's going to change in a 2 moles of NO2 to a 1 mole of N2O4 ratio. And then my chemical goes away. Moles go away. I'm going to be left with, oops, I shouldn't have crossed off the N2O4. I'm be left with N2O4 molar. I need to divide that in half then, which is going to give me a 0.0034 value that will fit in right here. Now that I know what my change is, I can take my initial value with my change to get my equilibrium value. So 0.0774 minus 0.0034 will be 0.074. These equilibrium values are what can then go into the equilibrium expression. Equilibrium expression, equilibrium values. You must have these E to go into your equilibrium expression. So therefore, K sub C is going to be equal to my NO2, it's going to go on the top, which is 0.0068, and that needs to be squared as it states in my expression. And then I'm going to divide that by the N2O4 value, and then I'm going to plug that into my calculator. Plugging that into my calculator, I get 6.24 times 10 to the negative fourth. But then I'm going to go back and look at my sig figs. The 0.0068 has 2 sig figs, so I can have 2 in my answer. 6.2 times 10 to the negative fourth is equal to K sub C. Box that answer so you can find it.